Section 5.1, Midsegment Theorem and Coordinate Proof. We're going to take a look at what a midsegment in a triangle is and also the theorem that goes with it. So, a midsegment of a triangle is a segment that connects the midpoints of two sides of the triangle. And every triangle has three midsegments. So if you look at this right here, M is a midpoint and P is a midpoint. So the segment MP is a midsegment. So MP is one of the midsegments. But if you look at the midpoint N right here with P, now you have another midsegment. You have NP. And finally, you have the midsegments of M and N, and also another midsegment MN. So every triangle does in fact have three midsegments. And when we draw them all in there, it does get somewhat confusing to have them all in there, but just remember that we find the midpoint using this midpoint formula. So we already have talked about that and used that, but if you were doing it in a coordinate plane, that's how you would find the midpoint. So what's the big deal? Well, if you take a look at this midsegment right here, NP that we did, how does it look like it might compare to side AB right here? We know one thing already. We know that because M is the midpoint right here, then we know that MB and MA would be the same. But what would that do to NP over here? What do you think that length would be compared? Or is there anything else that it looks like it might be? Think about that for a minute. And what it turns out is that the midsegment of a triangle is parallel to the third side and half as long. Parallel and half as long. And that's really important. Not only there are two parts to it. One part is that it's parallel right here. And the second part is that it is half as long. So DE, okay, we can see that DE is a midsegment. How do you know it's a midsegment? Because D is marked that way because you can see DB is one tick mark and DA is one tick mark, so that is a midpoint. E is marked the same way, so we see BE is the same length as EC, so E is a midpoint. So these are both midpoints, and those midpoints form this mid segment right here. And then we can see now it's marked this way, but because of that, then DE is parallel to AC. And DE will be half as long. So parallel is one part, but again, there are two parts, and the other part is that DE will be half the length of AC. And how would we show? How would we know? Well, we know parallel lines have the same slope. And we would use the distance formula right here that we've already been working on, not from the trimester, but in general. And we could, in the coordinate plane, could show that using the distance formula. And how would we show parallel? Well, remember, parallel lines have the same slope. And so we would use that slope formula right there to show that the lines are parallel and verify this. So one of the things I've noticed is that students tend to think about the midsegment and the midsegment theorem together. The midsegment is just what defines the midsegment of the triangle. The midsegment theorem is what the information tells us about each particular midsegment. So let's try to see if we can use that information to find some missing lengths and pieces here. So it tells us right here that MP is a midsegment of triangle LNO. So here's MP. Here is MP. These are all the same question. So we know that is a midsegment. They didn't show it by the markings on the triangle, but now we know that. So because it's the midsegment, what we know is that this will be parallel and this will be the same because these two are midpoints. So we already know that about the lengths. But then we also know that that midsegment is half as long as the side that it's parallel to. So that makes this 8 units. So MP is 8 units. Over here, now we're given that MP, again, is the mid segment. So that means the side that it's parallel to will be twice as long. The mid segment is half as big, and so the third side is twice as long. So that makes this X 14 units. And over here, again, it is the mid segment, so it's parallel to the third side, and it's half as long. But remember, it comes from these two mid points, so that makes this piece and this piece congruent, and as well over here for LO, so that makes this 4 units. So really that is just describing the features of not only a mid segment and what it means, but also if you're told that it is the mid segment, then you can use that information that it is parallel to the third side and half as big. So now let's apply to this particular problem. It says in triangle DEF, we can see that EJ is congruent to JF. Okay, they told us that right there. It tells us that FK is congruent to KD. So FK is congruent to KD. And DG is congruent to GE. So let's mark that. So now what we know is that all three of these points, G and J and K, are all midpoints by definition from what they told us. So we have 3 midsegments in there. So GJ right here, this side, I'll use a different color here. GJ right here, that side will be parallel to which side? Well, it will be parallel to DF. Because we know that G and J are midpoints, then GJ is a mid-segment, and it will be parallel to that third side. Okay, so now we want to know what segment is congruent to EJ. Well, here's EJ. What segment is congruent to? Well, it already gave us that it's congruent to JF, and we already marked it. But what other segment would it be congruent to? Well, remember, EJ is twice as long as GK. The mid-segment, this is a mid-segment, it's parallel to that side and half as long. So if this is 1 tick mark plus 1 tick mark, EF, then GK also has to be 1 tick mark long. So GK is also congruent. DE, let's take a look at DE. DE right here, this segment right here, is parallel to what? That's the third side, and it's parallel to this mid-segment right here. So that would be JK. And GJ is, we know, parallel, and it's the mid-segment of DF, or of the triangle, sorry. And so we know it's parallel to DF. And so GJ is going to be the same length as both of these pieces right here, because it's half as long. So that makes it DK congruent to DK, and congruent to KF. So now we can use some algebra to find some values of x and then find the actual lengths of these. So it says use the diagram of triangle XYZ where U, V, and W are all midpoints. So if it's a midpoint, remember what it does, okay? Remember that if U is a midpoint, these two pieces will be congruent. If V is a midpoint, then these two pieces are congruent. And if W is a midpoint, then these two pieces are congruent. And remember also that if we take a look at this segment and this segment, remember that UV, that mid-segment, is half as long as XZ, so that makes this also the same as each piece. So again, that's just overall what's happening here. So now let's see what the question asks. It says, if UW, so we're looking at this mid-segment now, if UW right here is 4x minus 1 and YZ, so this whole segment right here is 5x plus 4, what is UW? So we are trying to find that segment. Well, again, we know UW is a midsegment because it's formed by the midpoints. So what we know is that 4x minus 1 is equal to 1/2 of 5x plus 4. So we could just solve that. But we're going to end up with using distributive property, we're going to end up with fractions, which is fine. But remember that we could also say that 5x plus 4 is equal to 2 times 4x minus 1. And now we can eliminate those decimals and get 2, again using the distributive property, 2 times 4x is 8x minus 2 is equal to 5x plus 4. Now we can put all the x's on one side and all the numbers on the other, and that gives us x equals 2. So now when I want to find UW right here, I can simply substitute the 2. So I have 4 times 2 minus 1, and that would give me that UW is 7 units. So I found UW is equal to 7 units. I think I'll just circle this instead because it's kind of dark. So there we go. So then what about YV? So now they want us to find YV right here. Well, it is going to be the same because it's the whole thing is twice that of the midsegment. So it would be exactly the same 7 units. Or I suppose I could put it in there. I could take 5 times 7 plus 4 and then cut it in half, but it's really not necessary. All right, so here's where we start to think about proving something in coordinate proofs. It says, find the coordinates of the endpoints of each midsegment of PQR, and then use the slope and the distance formula to verify that the midsegment theorem is true for ST. So remember, we are going to find the coordinates of S and T and U. Now, it looks like we can just pick them out from the graph because the ordered pairs are actually marked there. But just to verify, remember, we would use the midpoint formula, which is the average of the x's, so 6 plus 0 divided by 2, and the average of the y's, 4 plus 2 divided by 2, to give us 6 divided by 2, or 3. 4 plus 2, 6 divided by 2 is 3, so S is 3, 3. So see if you can find the other coordinates of T and U right now. T would give you 5, 1, and U gives you 0, 2 if you did it correctly. And I can work out the details on the notes if you did not get those values. So now once we have those values of each of these, that was the first part. It says find the coordinates of the endpoints of each midsegment. So S and T are the coordinates of this midsegment. And T and U are the coordinates of this midsegment. And then S and U are the coordinates of this midsegment. So we have those three midsegments. So now what do we want to do? We want to verify the midsegment theorem is true for ST. So we want to verify for ST the midsegment theorem. Well, there are two parts that you need to verify. Remember, you're going to need to verify two parts. One, that ST is parallel to PR. That's one thing you have to verify. And the other piece you have to verify is you have to prove or verify that ST is equal to 1/2 of PR. So again, what we're going to have to do for that is we are going to have to find those pieces. So let's go back and let's verify the parallel lines, which means we're going to find the slope of ST and we are going to find the slope of PR. So we're going to use that y2 minus y1 over x2 minus x1 for ST. So for S we have 3, 3, and T we have 5, 1. So we are going to take, for ST, we're going to take 3 minus 5 over 3 minus 1, which gives us a slope of negative 2 over 2, which is a slope of negative 1. So my slope of ST is negative 1. That's a little messy. I'm going to try to clean that up a little bit. There. All right, so now let's do the slope of PR. So here's our points for P and R. So I'm going to take 4 minus 0 over negative 2. Oh, let's try that again. y2 minus y1, so I'm going to take negative 2 minus 2 over 4 minus 0, which is going to give me negative 4 over 4, which also gives me negative 1. So what I have shown is that the slopes right here are the same. So slopes are the same. So the lines are parallel. Now let's work on the distance formula. So for the distance formula for ST, I'm going to find ST by taking the difference in the x's, so 3 minus 5 squared, plus the difference in the y's, 3 minus 1 squared, which is going to give me negative 2 squared, which is 4. So negative 2, I'm going to have to square that, which is going to give me 4. And then I'm going to take 3 minus 1, which is 2 squared, which is going to give me 4. So I have the square root of 8. And remember, with simplifying radicals, that would actually equal the square root of 4 times 2. And then remember, we give them their own square root. And so we get 2 radical 2. So that is the length in units of ST. Now let's work on PR. So we have the difference in the x's again. So we have 0 minus 4 squared plus 2 minus negative 2 squared. So that's going to give me negative 4 squared, which is positive 16. This is going to give me positive 4 squared, which is 16. So that gives me the square root of 32. And so now, again, using simplifying radical strategy, we have 32 is 16 times 2. Again, using product property, that becomes 4 square root of 2 units. So now we can see from our work that PR is equal to 2 times ST, which proves that then that ST is equal to 1/2 of PR. Or either way, we could have divided by 2. So we just proved it since the slopes are the same, and since PR is twice ST, then now we know, we've just proven so now we know ST, the mid-segment theorem is true for ST. There. All right. Now, this was just verifying. We already knew the mid-segment theorem was going to be true, okay? But we're going to actually do this, proving it with variables in just a little bit. So what about the perimeters? Well, let's think about this for a minute. If we go back, the next question asks us about the perimeters. If we go back to what we know, again, about the mid-segment theorem, okay, let's go to this example right here. If GJ is half as long as DF, and all the mid-segments are half as long as the sides, doesn't it make sense that the perimeter formed by the, doesn't it make sense that the triangle formed by the mid-segments would be half as long as the perimeter of the actual triangle? And I think that makes a lot of sense. I'm not going to work out this problem right now in the lesson video, but I will work it out and show you how that works and maybe convince you that it will be true from the work. You might want to give it a try on your own first and then check back to the notes. So let's talk a little bit more about coordinate proofs. So when we do a coordinate proof, when we just verified the mid-segment theorem was true, we've proved that it was true for one example. That does not prove that it's true for every example. And that's what involves a coordinate proof. So a coordinate proof involves placing these geometric figures in a coordinate plane. And we're going to use variables to represent the coordinates, not just a specific example for every example that is placed in that particular position with those givens. So the first thing we're going to work on is just when we do that, we always want, when we're placing in a coordinate plane, we always kind of want to have one vertex at 0, 0. Whenever we place it in the coordinate plane, it's going to be more convenient and easier to prove if one of our vertices is at 0, 0. So we're just going to practice that for a minute here. It says, the first example says, we want to place a figure in the coordinate plane, assign the coordinates to each vertex, and we want a 4 by 4 unit rectangle. So we want to have, or 4 by 7. So we want to have 4 units for one side and 7 units for another. So notice that one of my coordinates is 0, 0. This coordinate right here is the ordered pair 4, 0. This ordered pair right here is the ordered pair 0, 7. And so then this ordered pair, I mean, it's easy when we have numbers, is going to be the ordered pair 4, 7. Now, we didn't have to do it that way. We could have placed it this way, where this was 4, and we went out 7, and that would be another way to do it. So we could have also flipped it and put it over on this side, but this was just one example. But again, the key is we want one vertex to be 0, 0. So when we go on to this next example right here, it says now we want a square with side length of s. So again, we want one vertice of the square to be 0, 0. And we know a square is going to have the same value, and it's supposed to be s units long. So it's s by s. And these two other sides are also S. So what does it make this ordered pair? Well, if S was 5, this would be 5, 0. If S was 7, it would be 7, 0. So this ordered pair is actually S0. This ordered pair is 0 S units. And this ordered pair, you're going out S units and up S units, so it is S, S. So those are the things we're going to be working on. So what I'd like you to do is I'd like you to try these two and then check back to the notes. And then I would like you to try this example right here, letter A, on your own right now. So again, we want 0, 0, and we want side lengths of P and Q. We don't know how long P and Q are, okay? But we want to put some orders, we want to find the coordinates here. So again, we just did this on the last example. This would be the ordered pair P, 0. This ordered pair on the y-axis would be the ordered pair 0, Q. And this ordered pair would be P, Q. Now you can do an isosceles right triangle, okay? So again, we always want one of our vertices to be right here. If it's an isosceles triangle, r units long, then both of these other sides of the triangle will be r. And so our ordered pairs would be r0 and 0r. So hopefully you're getting kind of the hang of it, because when we do coordinate proofs without actual numbers, like we did for verifying the mid-segment theorems, then we need to go back and use our formulas with variables rather than numbers. And that can get tricky. So again, this is just reminding us about a coordinate proof and what it involves. Now we're going to place a figure in the coordinate plane and assign coordinates again. But now we're going to find the length of the hypotenuse after we do that. So we just kind of did this on this last example. We know that we have an isosceles triangle with one vertice at 0, 0. And if the leg is C units long, then this vertice is going to be C0. And this vertice up here is going to be 0C. So how do we use that to find the length of the hypotenuse? Well, we use the distance formula. So to find the length of the hypotenuse, we are going to use the distance formula and take the difference in the x's. So we have 0 minus c squared and the difference of the y's, so c minus 0 squared. And so what that gives us is the square root of negative c squared, which is c squared, plus the square root of c minus 0, which is going to be c. When you square it, it's c squared. So what we get is the square root of 2c squared. But going back to our simplifying radicals, the square root of c squared is c. So this actually becomes c times the square root of 2. And if you're struggling with simplifying radicals, okay, go back and review your simplifying radical strategies. So now it says find the coordinates of the midpoint of the hypotenuse. So we want this midpoint. So we're trying to find m, the midpoint of that. So we use the midpoint formula. So we have to take the average of the x's. So we take 0 plus c divided by 2. And we take the average of the y's, which is c plus 0 divided by 2. So our midpoint, m, is the ordered pair c divided by 2, c divided by 2. Or sometimes it might be more convenient to write it as, since c divided by 2 is the same as 1/2 c, because there's a 1 in front, we could do the midpoint as 0.5 c, 0.5 c. All right, so let's try, this is a kind of a coordinate proof here. It says they give you the coordinates of the vertices of triangle ABC. They're already given there. So now we're going to prove that ABC is isosceles. So if ABC is isosceles, what I need to prove is that two sides are congruent and the third side is not. So I need to work on using the distance formula. So I'll find AC first. So AC is the square root of, again, the difference in the x's, so 0 minus negative h squared, plus the difference in the y's, so k minus 0 squared. Again, sometimes it can get tricky simplifying. 0 minus a negative h is going to be h squared. K minus 0 is k, so we get k squared. Now, I cannot simplify that anymore. That is the length. So it's that many units long. When you use the product property, okay, if this was times, then you could take the square root of h squared and the square root of k squared separately to get hk. You cannot do that when there is a plus sign in there. So AC is the square root of h squared plus k squared. That's it. So now let's work on finding the length of AB, because that's the ones to me that look like they're the same length, but we're not sure. So now again, I need to take the difference of the x's, so 0 minus h squared, plus the difference in the y's, k minus 0 squared. So that gives me the square root of negative h, or 0 minus h is negative h, but negative h squared is h squared. K minus 0 is k, square it, and you get k squared units. So we have shown that AC is h squared plus the square root of h squared plus k squared, and we have showed AB is the same. But to be thorough, what we also should show is that CB is not the same. So let's find the length of CB. So again, we take the difference of the x's, so we got negative h minus h squared. Difference in the y's, 0 minus 0 squared, so that's just going to be 0. So now, what I have here is negative h minus h is going to give me negative 2h squared. And so that gives me negative 2h times negative 2h is 4h squared. Now using the product property, I can take the square root of 4 and the square root of h squared separately. So what I actually get for this is 2h units. And so CB is not the same. CB right here, let's use a little bit different color here. Hopefully this one will show up better. So CB is 2h units. So now we have verified that these two sides are in fact the same. So this side and this side are the same. So since segment AC is congruent to segment AB, and they're both not congruent to CB, triangle ABC is isosceles. All right. So, given the coordinates of DEF and that G is the midpoint of DE and H is the midpoint of EF, I want to prove that GH right here is 1/2 of DF. So what I'd like you to do is I'd like you to try this on your own, and then I would like you to see and check back to the notes to see if you actually were able to prove it. Again, this is kind of tricky because you're using values. You're going to have to find G and H first. So you're going to have to find the ordered pairs using the midpoint formula. And then you're going to have to use the distance formula to find GH and to find DF. And that gets tricky when you have variables and then simplifying radicals and using those formulas with variables. So give it a try and see if you can verify it on your own, and then check back to the notes. This is the end of lesson